Hello and welcome to our electromagnetic analysis project. I'm Zak Scott.
I'm Christian Whitesides.
And I'm Anthony Boyd, and today we'll be exploring magnetism, more specifically how it is closely related to electricity.
But first, a little background on our project. Humans have been fascinated with electromagnetism ever since the first electromagnet was created by William Sturgeon in 1825. This is most likely due to the fact that electromagnets create a force that acts on metal without anything touching it. This illusion of having free-floating metals or invisible forces opened a lot of possibilities for engineers and scientists. In today's modern world, we use electromagnets in MRIs, cell phones, levitating trains, and much more. Electromagnets provide the potential to create frictionless systems, which have allowed for countless breakthroughs in the realm of engineering and science. Some of the world's most advanced electromagnets are used in huge labs for scientific study. One of the best examples of these is the Large Hadron Collider in CERN, Switzerland, used to maneuver extremely small particles at the speed of light. However, to use these tools effectively, we need to be able to predict their behavior and plan ahead using mathematical formulas. Throughout this project, we have worked to create an equation that measures the force of an electromagnet.
The equation we utilize for this project is F equals Ni squared times mu times A, all divided by 2G squared. In this equation, N is the number of loops, I is the current, mu is the permeability of the metal, and G is the distance between the magnet and the metal. A is also the cross-sectional area of the core. This equation is known as Maxwell's force formula, just one of Maxwell's equations. In order to derive this equation, we need to start with B equals mu times I times N, all divided by G. In this equation, B is for magnetic field in Teslas, mu is the magnetic permeability of the environment, and I is the current in amperes, while G is the gap between the object and the magnet. From this, we plugged in our equation for B into Maxwell's force formula of F equals B squared times A divided by 2 mu to get F equals Ni squared mu times A, all divided by 2G squared. This is after some simplification. This equation was derived from the Lorentz force law, where F equals QV times B, where the force is equal to the movement of charge times the magnetic field. How Maxwell got this equation is through a system of differential equations that accounts for all the charge moving through a wire wound in many loops.
The equation mentioned earlier is derived from Faraday's law. It shows the relationship between volts and magnetic flux. Admittedly, this is a simplified model of the real force of a magnet. This is because irregular shapes of metal can cause these equations to fail. However, we will be using these equations in an example where a flat disk of metal is being placed in a way that the electromagnetic field is almost uniform. As a result, these equations can be used as a builder's model for predicting the force of a magnet. The variables of the equation can be adjusted to fit a variety of applications and resources. In real-world manufacturing, the common use of these materials is an iron core, wound by a copper coil that is packed as tightly as possible. Real-world amperages of magnets range from the 0.63 amps on 2-inch diameter magnets up to the 200 amps seen on a modern MRI machine. Quickly, magnets can become very powerful. This may be because of the availability of copper wire. A great conductor in a perfect wire can be wound hundreds of times, increasing the N in Maxwell's equation dramatically.
We examined two different electromagnets. For our first magnet, we were given the size and shape of the magnet online and used it to calculate force. Additionally, we were given the rated DC and amperage to be 12 volts and 0.68 amps. Furthermore, we assumed that the core was made of iron, and we will use 6.3 times 10 to the negative 3 as our permeability that will fill in for mu. To figure out how many loops there were, we took the cross-sectional area based on the 2-scale image we found online and used it to calculate how many loops of copper wire could fit within this cross-sectional area. We assume that they were using 20 gauge copper wire, a small diameter wire that is common for a magnet of this size. Furthermore, we calculated the radius of the core to be 5 millimeters, and therefore we will plug in for pi r squared to make our cross-sectional area. Thus, the equation F equals Ni squared times mu times A, all divided by 2g squared, can be now filled in to create 0.358 newtons of force. This measurement was taken at 10 centimeters for our G.
Our second electromagnet comes from a Sony speaker. We dismantled the speaker in order to find the electromagnet. In this case, power equals 0.4 watts and resistance equals 8 ohms. In order to find current, we are going to use the equation power is equal to current times the change in voltage. Now, we don't know what the change in voltage is, so we're going to use the formula delta V is equal to current times resistance and use that formula to substitute it into our power equation. Now, power is equal to current times the resistance. And once we rearrange that formula, current is equal to the square root of power over resistance. We then substitute in our variables, and current is equal to 0.2236 amps. Now that we know what the current is, we can go on to find the force of our electromagnet. Assuming that the core is made of iron, our mu is going to be the same as our last example of 6.3 times 10 to the negative 3 for our mu value. We found that the coil has 60 turns, or N equals 60 turns of copper wire, and our G value is going to be 1 millimeter. And we found that the radius was 7.25 times 10 to the negative 3 meters, or 7.25 millimeters. And to calculate the area, we're going to substitute that radius into pi r squared. We then substitute all these variables that we just found into our force equation and find that the force is equal to 93.623 newtons.
Over the course of our project, we learned where electromagnets originated from, and by deriving Maxwell's equations, our group's understanding of the equations and mathematical relationships involved in electromagnetism has increased. Our group now feels confident in our ability to further analyze and understand electromagnets as a result of our research and applications. Thank you for watching.